Hi everyone, and welcome to the lecture on conversion factors and dimensional analysis. Dimensional analysis is a unique problem-solving method in which we can set up units so that we can cross-cancel them, deleting all of the units that we don't want and leaving only the units we desire. We do this by setting up conversion factors so that we cross-cancel all of the units. In order to set up a problem, we're going to identify the known that's given, that is the quantity and the units. And we're also going to identify the units of the unknown quantity. We'll write down the known quantity and units on the left side of our paper and the units for the unknown quantity on the right side. And then we multiply a known series of conversion factors so that we can cross-cancel the units we don't want, leaving only the units we're after. And then lastly, we perform the mathematical operations that are indicated by the conversion setup. So let's give this a try. Suppose we wish to convert 25 miles to kilometers. And we have a conversion here, some tabular data that we don't know where it came from. 0.6215 miles in a kilometer that's given to us. We know that we have our 25 miles. So we're going to write that down on the left. And we're after kilometers, so we're going to write that down over here on the right. And we're looking for conversion factors to take us from miles to kilometers. If we're cross-canceling, that means that we need to put miles on the bottom here so that we can cross-cancel from the top to the bottom. We know that when we have any number over 1, that number is just itself. So that tells us that those miles are on the top. We have 0.6215 miles in 1 kilometer. We've cross-canceled the miles, and we know that we have kilometers on the top. That's what we want. So now all we have to do is solve this problem. We put it into our calculator as 25 divided by 0.6215. And I get 40.2252614.6. And of course, the units are kilometers. And now I'm going to evaluate my significant figures and make sure that I can answer this question to the correct number of significant figures. The only data I have is this 25 miles. As I told you, the 0.6215 miles in a kilometer came from tabular data of conversion factors of English system to metric system. My data value is 25 miles. That's the value I'm going to use for my significant figures, and it has 2 significant figures in it. If that's the case, I need this significant figure and this one. I'm going to evaluate the next digit over. Is it 4 or less, or 5 or greater? And of course it's 4 or less. So that means that all of these values are going to go, and I'm just going to keep the 4 and the 0. But in order to make sure I'm showing that I have 2 significant figures, I'm going to have a decimal in this number, or the trailing 0 won't count. So I put the decimal right after the 0 and the 40. The other way that I can do this is to convert it into scientific notation. If I convert 40 into scientific notation, that means that I'm going to get a number between 1 and 10, so greater than 1 and less than 10. One place is what I move, so that is going to be 4.0 times 10, and I only moved one place, and that exponent is a positive 1 because the value that I started out with was not a decimal number. Let's look at some conversion factors and see if we can write those conversion factors so that they're useful for us regardless of which direction we want to go for cross-canceling. So we could write 4 quarts per 1 gallon this way, but if we wanted to go another direction to cross-cancel, we could write 1 gallon for 4 quarts this way. We could write 8 fluid ounces per 1 cup like this, but we could also put 1 cup on the top and the 8 fluid ounces on the bottom. And I'll leave the last one for you. Here's a your turn question. And I'm going to leave that for you to do later, but I just want to point out to you that when we're looking at these conversion factors, this is one part of our conversion factor. This is the other part of our conversion factor. We can either have the 1 kilogram in the numerator or in the denominator, but we have to make sure that we put the 2.205 pounds adjacent to it, whichever direction we decide to go with that. Let's look at this question. How many seconds are in 2 weeks? So the only thing that we have here is the 2 weeks. So that's what we're going to start out with. And I'll put that over on the left side. Ultimately, we want seconds. So I'll put those seconds over here on the right side, and I'll just put a question mark next to them because that's what I'm after. Now they're giving us 1, 2, 3, 4 conversion factors going from weeks to days, days to hours, hours to minutes, and minutes to seconds. So that should get us where we want to go. We're going to start off with a conversion factor that puts weeks on the bottom so that we can cross-cancel them. And we see that we go from 1 week to 7 days. So we can use that as our first conversion factor. And now we want to get rid of days. Since it's on the top here, we're going to put it on the bottom in the next conversion factor. And we see that we have a conversion factor that goes from 1 day to 24 hours. Our next conversion factor is going to have to put hours on the bottom to cross-cancel that. And we see we have a conversion factor going from hours to minutes. So 1 hour is 60 minutes. And now we want to cross-cancel minutes. So that goes on the bottom of our next conversion factor, which shows 1 minute is equal to 60 seconds. And now we go back through everything and make sure that all of our units are cross-canceling, just to double check and make sure that we set everything up correctly. Now we just do the math, and so into your calculator, that's going to be 2 times 7 times 24 times 60 times 60, and I get a pretty big number of seconds, 1209600 seconds. Now we have to evaluate our significant figures. We only have the one data value right here, that's the 2 weeks, and that is 1 significant figure. Sorry about that. There we go, 1 significant figure. So that's this guy right here. We're going to evaluate the 2, which is 4 or less, meaning that we would normally drop all those numbers, but we can't do that because if we drop all those numbers, we're going to end up with just 1. And we know that we have a fairly large number. In fact, this is 1,209,600. So we can't substitute that with just 1. We have to keep all of those digits as placeholders. That means that we're going to have 1, 2, 3, 4, 5, 6 zeros. And rounded to the correct number of sig figs, we have 1 million seconds. How many centimeters are in 12 millimeters? Again, we know that we only have one value we need to start with, so we can write those 12 millimeters down here on the left, and we're after centimeters, which is going to go over here on the right. We don't know anything else, so if you don't know how to get started with this, you do know one thing. You want to cross-cancel millimeters, so you're going to put that on the bottom. And if you memorized your metric system, you know a power of 10 that relates millimeters back to the base unit for length, and that is meters. We're always going to put a 1 by the prefix, and the prefix in this case is milli. So we put a 1 by the prefix, and up top we put the power of 10 that's associated with milli, and that is 1 times 10 to the minus 3. Our next step is going to be to cross-cancel meters. So we know we can go from meters, which is the base unit, to centimeters because we know a power of 10 that we memorized to get from the base unit of length in the metric system to any of the prefixes. Again, we put a 1 by the prefix, and in this case, the prefix is centi. And then we put the power of 10 by the base, so that is 1 times 10 to the minus 2, which is the power of 10 for centi. And now we double check to make sure that we can cross-cancel everything. So we cross-canceled millimeters, we cross-cancel meters, we're left with centimeters. It's on the top, so that's what we're after. So our units are set up correctly. Now we just need to solve the math. Because we have scientific notation here, I'm going to show you how to use your TI-30XA calculator, which is why I asked you to buy, one of the reasons I asked you to buy this specific calculator, so that I can show you all at the same time how to use it and get this calculation done. So we start with the 12, and then we multiply that by 1. And then find on your calculator the EE button. That EE button is your exponent of 10. We plug in the coefficient and then the EE button, and in this case the coefficient is the 1. EE and then times 1, so we don't have anything else that we need to do there except for the exponent, so that's 3. And then if you look at the bottom of your calculator next to the equal sign, you'll see a plus minus sign. That will, if you push that, that's going to make your exponent negative. Then we need equals, and then we're going to divide by whatever's on the bottom. And on the bottom we have more scientific notation. So that is 1, which is this one right here. I'm skipping this one because multiplying anything by 1 is going to be itself. So we have 1, which is our coefficient on our scientific notation, EE, and then the 2, and then plus minus, and now it's equals. And so we use the calculator exactly the way that's written out. It is 12 times 1 EE, 3, hit the plus minus key, and then equals, then divided by 1 EE, 2, hit the plus minus sign and equals, and I get 1.2 centimeters. Now this EE key that you're hitting, that takes care of the 10 value. So don't be plugging in 10s, plug in your coefficient, which in this case, both times the coefficient is a 1. So that's why we plug that in. Now we look back at our significant figures and we see that we have 2 non-zero digits, so that's 2 significant figures here in 12 millimeters, and we have 2 significant figures here in 1.2 centimeters, so this is our correct answer. The next question is a little tougher because we're looking at cubes here. So we're interested in finding out how many cubic centimeters there are. So we're going to put that over here on this end. In 12 cubic millimeters, so that's what we're going to start with over here. 12 millimeters cubed. Let me just erase that. And put another one there. So 12 cubic millimeters. The first thing we know that we need to do, if you don't know how to get this started anyway else, you do know that you want to cross cancel millimeters because we're after centimeters. So we're going to put millimeters on the bottom. We know a power of 10 that relates millimeters back to the base, which is meters. And we're going to put a 1 by the prefix, which is milli in this case, and the power of 10 goes by the base. And that is 10 to the minus 3. We also know that we're going to have to cube this. We don't want meters, and we currently have meters on the top because we're going to cross cancel milli down here. So we need to get rid of the meters. We're going to put meters on the bottom. We know a power of 10 that relates meters, the base unit, back to centimeters. So we can go directly there. We put a 1 by the prefix, which in this case is centi, and the power of 10 for centi goes by the base. 1 times 10 to the negative 2. And we know that this has to be cubed. Now, in order to cube those exponents, we have to apply them not only to the other exponents, but also to the units down here. Because this is a 1, 1 raised to the power of 3 is still 1. But we do have to apply that 3 to those units and cube them. Again, this is a 1, and so 1 raised to the power of 3 is still 1. But we do have to cube those units, and we have to cube the units on the bottom, as well as apply that to the exponent that's on the bottom here. To apply those exponents that are outside the bracket, we're going to multiply them. So we have 12 millimeters cubed times. On the top, that is 1 times 10 raised to the 3 times negative 3, which gives us a negative 9, and then that is meters cubed over. And on the bottom, we have 1 millimeter, and we apply that 3 that's outside the parentheses, and we get millimeters cubed. Now the next parentheses, that's a 1, so 1 cubed is still going to be 1, but we have cubic centimeters on top now. And then on the bottom, we have 1 times 10 to the negative 2 times 3, which gives us negative 6, and we have meters cubed. And now we can look at things to make sure that everything we don't want cross cancels, leaving us what we do want. Millimeters cubed cross cancels, meters cubed cross cancels. We're left with centimeters cubed. That's what we're after. So now all we have to do is the math. In your calculator, that's going to be 12 times. Again, this is scientific notation, so the coefficient is 1, and then EE, and then 9 plus minus to get that negative sign on the exponent, then equals, and then we're going to divide by what's on the bottom, so our coefficient is 1, then EE, then 6, and then plus minus, and then equals. And when I calculate this, I get 0.012 cubic centimeters. And when I look at my significant figures here, I know that this is my only data value that is 2 sig figs, and I have 2 significant figures here because leading zeros don't count as significant figures. Now you notice that on this slide, which is the solution, they've given you the answer here in scientific notation. So you can use your calculator to get from 0.012 to scientific notation simply by clicking on the button that says second, the yellow or green button at the top, and then the number 5. And you notice you'll see 1.2 and then raised to the power of negative 02. That means 1.2 times 10 to the minus 2. That's the meaning of what you're seeing. You can go back to standard numerical notation by hitting second 4. And now you can see that you get 0.012. You also know how to go back and forth between these values manually. So let's talk about temperature and temperature conversions. We need a definition for temperature, and that is the measurement of the intensity of heat. And if we're going to have a definition for temperature that includes another term that we don't understand, we need a definition for that term, and that is heat. So heat is a form of energy that's associated with the movement of particles. And the movement of particles is associated with kinetic energy. And we'll talk more about heat, light, electricity, potential, and kinetic energy later. But it's important to know that nearly all changes that matter undergoes involve some sort of release or absorption of one of these types of energy. There's 3 different scales of temperature that we're going to look at, but we're mostly going to use Celsius. We will use Kelvin when we get to gases. You cannot calculate gases without using Kelvin scales, and we'll talk about why that is when we start talking more about gases. In the lab, we have a tendency to use Celsius because the thermometers that we have measure Celsius. And I'll point out to you right now why we like Celsius and Kelvin better than Fahrenheit. If you look at the boiling point of water, or literally you could look at the boiling point and freezing point of any substance, but if we look at water, the boiling point in degrees C is 100, and the freezing point of water is 0 degrees C. That's a 100-degree spread for Celsius. Now, if we look at Kelvin, the boiling point of water is 373 kelvins, and the freezing point is 273 kelvins. Again, 100-degree temperature spread with both Celsius and Kelvin. Fahrenheit, on the other hand, you don't have that spread that's 100 degrees. You have 212 degrees Fahrenheit for boiling and 32 degrees for freezing, and that makes Fahrenheit a temperature scale that's a little bit more difficult to do calculations with. So ultimately, we like Celsius better, just like we like the metric system better. Both of them make things easier for us to calculate data. When we are doing temperature conversions, we have a few different formulas, and students often ask me, do I have to memorize these formulas? And the answer to memorizing formulas and constants is no. I will always put formulas and constants on the test for you, usually on one page. So you need to sort of know, have a little bit of an idea what you're looking for, but it's recognition, it's not memorization. So if you want to calculate Kelvin from degree C, you simply add 273 to your degree C temperature. On the other hand, if you want to calculate degree C from Kelvin, you subtract 273. And I'm going to give you a hint right here and tell you that Kelvin is always a positive scale. So if you ever get a negative value and you're calculating Kelvin, you know that you went the wrong way with that 273. Fahrenheit or degree C can be calculated with this last formula. Fahrenheit equals 1.8 times a degree C plus 32. And again, we can use that formula to calculate either one of them. So let's convert 90 degrees Fahrenheit to Kelvin. And in this particular example, we can't go directly from Fahrenheit to Kelvin. We're going to have to go through degrees C. So we're going to calculate degrees C from Fahrenheit. That's the first thing we're going to do. And again, we only have one value and one set of units. So that's what we're going to start with. So we have 90.0 degrees Fahrenheit to start with, and that equals 1.8. I'm just plugging into this bottom formula right here, times degrees C plus 32. Let me just erase and start over because it's okay. Simple algebra, what we're going to do to start with is subtract 32 from both sides. So 90 minus 32, which you should be able to do in your calculator, is going to give you, or at least I get, 58, which equals 1.8 times degrees C. And now I'll just divide the 1.8 out of both sides. And I get this number 32 with all of these trailing 2's. And that is degrees C. Now, what I really want to do is go back and look at the question that I'm being asked. And the question, I always want to do this in chemistry because a lot of times students will stop at the degree C answer, and if it's a multiple choice, that degree C answer is going to be there to accommodate you, just to make sure that you're thorough and you're going back to look at the question you're being asked. Because for scientists, it's very important that we don't stop prematurely. I want to go from Fahrenheit to Kelvin, so I'm not done yet. So I'm going to take that 32.22222 degrees C, and now I'm going to add 273 to get to Kelvin. Okay, so I still have that 32.22222 forever in my calculator, so I just say plus 273, and I get 305.222, and again, those are trailing, but this is Kelvin this time. And now I just want to double check my significant figures and make sure that I'm using the correct sig figs. The only data value I have, I'm not going to use anything from up here. I'm not going to use these formulas because these are static constants that are in these formulas, so I'm not going to use those. I'm going to use my data value. The only one I have is 90.0. Because there's a decimal, the trailing zeros count. So this is 3 sig figs. So 1, 2, 3 sig figs is what I need. I look at this digit, it's 4 or less. So I'm going to just drop all of those digits, and my answer becomes 305 Kelvin. And here is the solution. And here's another one. This is a your turn. So I'm going to leave you to solve this one, but I just want to point something out to you so that you're clear. There is a decimal here. So that makes this 303 sig figs. That brings us to evaluate density. Density is a ratio of mass over volume, and so you'll often see it written like this in a formula. And you can see that we're saying if you have a higher temperature, the density decreases while the volume increases. And so let's just think about why that would be the case for a minute before we go on. So again, they're saying the volume increases. Well, if we put a beaker filled with water to the very brim over a Bunsen burner and light the Bunsen burner and start heating the water, eventually the water is going to undergo thermal expansion, and it's going to start to boil over the top edges of the beaker. In other words, the volume increased. If we increase the denominator of a fraction, and let's just try this, and we maintain the numerator, so if we had 1 over, let's say, 2, and then 1 over 4, and then 1 over 8, and then 1 over 16. So we're just increasing and increasing that denominator, and we see what happens to the entire ratio as we do that. As we increase the bottom, what we're doing is decreasing the ratio. that ratio is equal to the density. And so that means that the density is going to decrease if we increase the denominator of mass over volume. Likewise, we could look at this from another point of view and say, okay, then what happens down here to the density, mass over volume, if we decrease the volume? And if we do that, if we decrease the volume, that is like going exactly the opposite direction that we just went. And so that is like going this way. And if we go that way, then you can see that we are increasing that ratio that equals the density or the value of density. And then the last thing that I want you to realize is that I gave you a couple of numbers. I don't want you to memorize them with the exception of maybe this one, because we use this one quite a bit, that the density of water is 1.0 grams per mil, just as a reference value when we're not getting an exact density at the specific temperature that the room is. But you notice that the density up here, where we increase the volume, is lower. It's 0.9718 grams per mil, where if we decrease the volume, then the density increases and we get 1.0 grams per mil. Extensive versus intensive properties are fairly straightforward. When we're looking at mass and volume, they are dependent upon amount. So for example, if I have a beaker that is a 50 ml beaker, and I have another beaker that is a 100 ml beaker, and I fill both of them to the rim with water, clearly this beaker is going to have a higher mass compared to this beaker, which would have a relatively lower mass. And so the amount, the mass, and the volume are dependent. That's an extensive property. Density, on the other hand, it doesn't matter if we have one drop of water or a whole swimming pool of water. If that one drop and that pool are at the same temperature, then the density is going to be the same for both of them. That's an intensive property. So they don't depend upon volume or mass. The density doesn't depend upon volume or mass. Density does depend indirectly on temperature. And so I'm just going to write that in here, indirectly. And the reason I say indirectly is because density equals mass over volume. So you notice that temperature is not one of the species in that formula. So indirect relationship means that the temperature impacts something in that formula. And we just evaluated this on the previous slide, and we saw that volume could be impacted by temperature. And when the volume is impacted by temperature, it either increases or decreases. If the denominator of this ratio increases or decreases, then the density is going to increase or decrease also. Let's do a density calculation. And again, I want you to get used to writing down what your units are, because if you always write down what your values and your units are, then you're going to be much more capable of evaluating things to see if you can solve it quickly or if it's going to take another step for a conversion. So we have 63.956 grams. That's one of our values in this question. The other one is 50.0 mils. And if we evaluate those units, then we know that we have grams and we have mils. And density is mass over volume, and the mass can be represented with grams and the volume can be represented with mils. And so we don't have to do any conversions associated with this calculation. In fact, it's fairly straightforward because we can just plug in 63.956 grams over 50.0 mils, and then do the calculation, we know our units over here are going to be grams per mil. And what I get here is 1.27912. And so we have to evaluate our significant figures. We have two data values, mass and volume. In the mass, we have 5 sig figs. And in the volume, we have 3 sig figs. The trailing zeros count because there's a decimal. So our answer, this is division rule, multiplication division rule, our answer is going to have the same number of sig figs as the data value with the least number of sig figs. So that is 3. So that will be here, here, and here, meaning we're going to evaluate the next one over, which is a 9, and that is 5 or greater. So we will increase our last retained digit by 1 and then drop the others, and that gives us 1.28 grams per mil for our final density value. And so here's another your turn that I'm going to leave for you to do later. And the solution is there in case you get stuck. And then I want to go over this problem because it's a little tougher, this problem. So as we go through it, we read through it, we're going to sort of underline what's important here, and then we're going to make ourselves a list. So crash sounds from the lab, a large vial of mercury has fallen from a broken shelf. We call the hazardous materials team to report the spill, which is about 2 quarts of mercury. And so I'm going to write that down, 2.0 quarts, and I'm just going to give the chemical symbol for mercury. They ask for the mass, and so I know that this is what I'm after. So down here, I'm just going to take a note that I'm looking for the mass of the mercury. You determine there are 1.0567 quarts in a liter. And again, this is a conversion factor that I looked up on a table. That's how I determined that. So 1.0567 quarts per 1 liter. And then you look up the density of mercury in a CRC index or a Merck index, and I get that it is 13.69. You notice how much more dense that is compared to water, which makes perfect sense if you've ever held mercury in a bottle. It's very heavy. So 13.69 grams per mil, and now I'm going to start evaluating what I have in terms of units. So I have quarts here, and then I have quarts that takes me to liters here. So those quarts will cross cancel. I'll get liters, but ultimately I'm after mils. The good news is that I know a power of 10 associated with the metric system that can get me from liters to mils. So that won't be a problem either. And then ultimately I'll have grams left over that won't cross cancel. So I'm going to start with the simplest, most straightforward value in units I have, and that is 2.0 quarts of mercury. And that's the simplest because I don't have units on the top and the bottom. The other two I have units on the top and the bottom, so those are more complicated. First thing I know I need to do is get rid of the quarts. So they're going to go down on the bottom. And I have this conversion factor that 1.0567 quarts is in 1 liter. And now I know that my quarts are going to cross cancel. And I currently have liters, which is not what I'm after. So I know that I need another conversion factor, and if I have to cross cancel liters, they're going to go on the bottom. I know a power of 10 that relates back to the volume base of liters for mils. So I can go from liters to mils. I'm going to put a 1 by the prefix, which is milli, and then the power of 10, 1 times 10 to the minus 3 for milli goes by the base unit, and now I'm cross-canceling liters. I have mils. I don't want mils because they're asking me for the mass. I go back to the question, look at the question, and I say, I don't want mils. They're asking me for the mass. That means mils have to go on the bottom because I have to cross-cancel them some way. I have density over here that has mils in it, and it also has grams in it. So I can go from mils to grams using that conversion factor, and it is 13.69 grams in 1 mil. Now my mils are going to cross cancel and I will be left with grams on the top, and that is what I'm after. So all I have to do is the math at this point. So that math is going to be in my TI-30XA calculator like this: 2 times 13.69, because we don't need to multiply everything by these ones, equals, and then it's going to be divided by, I need to open parentheses because it's divided by a product. It is not divided by 1.0567 and then that value divided by 1 times 10 to the minus 3. Your calculator will do it that way if you don't use the parentheses. So we need to open the parentheses, and then it's 1.0567 times, and we have scientific notation. So that is the coefficient is 1, EE, 3, and then hit your plus minus key so that you can get a negative on that exponent. Close your parentheses, and then equals. And when I do this math, make sure you hit your parentheses buttons on your calculator. I get a pretty large number, 25910.85455. Okay. So now, and that is grams, and I'm going to squeeze the grams in here. Now I want to check my significant figures to make sure that I have those correct. I look at the data values that I have, and there's honestly only one data value, and that is the 2.0 quarts of mercury that I have. I looked the other values up. I looked up this conversion factor for a quart conversion to liters, and I looked up the density. The reason I don't want to use those, they're not data values, is because if I look something up, I didn't get that value in the lab using my equipment. So I have no idea what the precision is, and that precision definitely doesn't match my data values. The only data I have is my measurement of the quart, of the quarts of mercury. So that is 2.0, that is 2 sig figs. So I'm going to come down here, and I want the 2 and I want the 5. So I'm going to evaluate the next one over, and that is 5 or greater. So I'm going to have to increase the last retained digit by 1. That's going to be 26. Well, I can't stop at 26 clearly because this value is 25,910. 26 is nowhere near that. So I'm going to have to add zeros for the rest. They won't count as significant figures because trailing zeros are not significant figures. So that leaves me with 2 significant figures and the correct mass that I need. And you can see that here they've written it in scientific notation, which is fine. Also, you can convert it to scientific notation. And then the last one, this is a your turn for a density, and I'm going to leave that for you to work out. And that is the end of our density lecture. So hopefully you were writing down all of those notes as I was going through. And this will be posted right away.